Hi. Now I am going to talk about Minkowski's space-time diagrams, world lines, events, and light cone of an event. What is a Minkowski space-time? Minkowski space-time is a graphical representation of events and the motion of particles. All those things can be represented here in Minkowski space-time. And in physical space or in an inertial reference frame, we will be having coordinates like x, y, z, which represents position of a particle. And similarly, in Minkowski space-time, we will have x, y, z axis also, plus along with that we will have one more extra axis which will be time axis, which will actually count the time and which will represent time. An event is actually a thing which happens somewhere at some time, and an event needs two quantities to represent it. One is at which location it is happening and at what time it is happening. And Minkowski's space-time appropriately suits to represent these events. That's why in Minkowski space-time you will have time as one more extra axis. Along with the physical axis xyz, Minkowski space-time will have one more extra axis to represent time. Now we will see how it is. Here we will consider an example of one-dimensional case. One-dimensional in physical system. One-dimensional means the motion is restricted to only one dimension. Here I am considering that as x-axis here. So now consider, say there is a particle which is located at the position 5 on the x-axis, and in Minkowski's space-time diagram that same point will be represented on x-axis at 5, and also since it has one more time axis, you can read that the time here is 0. So now if I change the time to certain value, say it is 4 seconds, then now you see that the point represented by the particle in the Minkowski space-time also changes. So why it has to change? Because it has to take care of the time also. So now in a way that this point B is at position 5 in the physical reality, and the time now is 4 seconds. So now, then in Minkowski space-time, the position of this particle in this Minkowski space-time is represented by this coordinate, the one which you are seeing here. So now if you read it, its x coordinate is 5 and its time coordinate is 4, which means that the particle at 4 seconds is at position 5. And any point in this Minkowski space-time represents an event. An event which is having two informations. One is the time at which the event is happening and the position at which it is happening. And now the trajectories of the particles represented in Minkowski space-time are called as world lines, which means that here, for example, I will consider the trajectory of the particle B in Minkowski space-time. Let B be a stationary particle, means which doesn't move even if the time changes. You may ask, if the particle B is not moving, then where is the trajectory? What's the question of trajectory? Trajectory means it is the curve on which a particle moves. Of course, the particle is not moving in the real space, in the real inertial reference frame, but in Minkowski space-time, in the Minkowski's representation, that particle will move. Sorry, it's not the particle which move, the point represented by the particle in Minkowski space-time will move. The particle will be stationary, but the corresponding point in the Minkowski space-time is going to move. Why it has to move? Because even though the particle is at rest, the time will be still ticking. So the time will elongate the trajectory of it and it will show a curve in the Minkowski space-time. Now we will play the time. See, now it's the particle B is at rest at position 5, but since the time is ticking, it is dragging a curve in the Minkowski spacetime. So this curve, this trajectory, which is represented by the particle in the Minkowski spacetime, is called as an word line. Right, this is the word line for a particle which is at rest. Then what will be the word line of the particle which is moving? So we will consider a particle which moves in the real one-dimensional way. One-dimensional means the motion should be restricted to only along x-axis. So consider a particle d which moves along x-axis, and we will see how the curve is traced in Minkowski spacetime. So now you can see that as the particle d is moving along the x-axis, its exposition is changing in the Minkowski spacetime, as well as its time also will be changing. So an uniformly moving particle in one dimension will actually represent a straight line with certain slope in the Minkowski spacetime. This is for a particle which is moving at some slow speed, some moderate speed. Of course, it is relativistic. Now we will see two particles. One is slower than the other particle. How the word lines of those two particles will show up in Minkowski spacetime. You can see that the particle d, which is moving slower than the particle a, will actually have a larger slope compared to that of the fast moving particle. A fast moving particle will have lesser slope, and the particle which can move at maximum possible speed is none other than the light. The light will travel at the maximum possible speed in the nature. So right now, if this is the scenario, then how will be the trajectory of a light? And compared to the particles, the fast moving and slow moving particles, the trajectory of the photon in the Minkowski spacetime will have slope equals to 1. That's how the Minkowski spacetime were constructed out. And now you can see that the photon will have the lowest possible slope in the Minkowski spacetime, and all other particles will have larger slope compared to that of the photon. So now then, what will be the word line of a particle, word line of a photon which is moving backwards? Now you can see that the word line of the photon which is moving backwards will show up with a negative slope on the other quadrant. So now you can see in this diagram, this is the word line of the photon which is moving backwards. You might have observed here, the CR is the photon which is moving backwards, and the photon which is moving forwards. Now you can see that the forward moving light and the backward moving light forms two straight lines with the slope equals to 1 in the 1 and minus 1 in the Minkowski spacetime. And you can see that there is an appearance of a wedge-like or a piece of a cone in the Minkowski spacetime. You can see this saffron line here of the photon. This looks like a cone. This looks like a cone. I will remove the particles and I will show you only that of the light. Right, now you can see that these two are the word line of the photon emitted by a single point. From the photons emitted in both the direction from a single point traces two straight lines, and those two straight lines forms a piece of a cone. A piece of a cone means it's a cross section of a cone which will be a wedge. So in two-dimensional Minkowski space or in one-dimensional physical system, the envelope of these two word lines will form a wedge. And now if you extend it to one more, So you will see the light cone of an event. I will show you soon. And now, since no particle can travel faster than that of the light, all the word lines will have slope in such a way that they will be within this, the word lines of these photons. So now we will see the three-dimensional extension of the word lines of photons. Now consider there is a event A, and event A is happening in a two-dimensional world. So two-dimensional world means here it will have two axes, x and y, and here you are seeing in the right hand side a Minkowski's spacetime representation of this event A. So this dot A dash represents the event which is happening at this location A, and from this event, if the photons are emitted out in all the directions, then what will be the word line of those photons in the Minkowski spacetime? So we will see what they will be. So now you can see that these green dots are the photons which are moving away from that point A, and each photon will trace a straight line in the Minkowski spacetime, and you can see that it forms a cone. Means, of course, you should have still so many dots to have complete cone. I have just interpolated it. So hence the photons which are emitted from this point collectively forms a cone in the Minkowski's diagram. You can see this is the cone formed by the word lines of photons emitted from this point A. Right. So now next thing is the light cone of an event, and from which how we talk about the past, present and future. You might have heard some words like absolute past, absolute future and absolutely separated events. So we will consider two events, E1 and E2, and we will discuss whether the event E2 is the future of E1 or the past of E1, or both E1 and E2 are absolutely separated out. So now to analyze this, word lines of the photons emitted from these events, which forms a wedge or the light cone, will help actually. So the light cones of these two events will actually help us in analyzing the events. Now consider, say as an example, let event E2 is birthday of a mother, and let E1 be the dispatching of gift to that birthday from a daughter. Both daughter and mother are living in two different planets, and they are separated by a large distance. Now the thing is, the birthday E2 event, is it future of E1 or is it past of E1, or is it absolutely separated out? Of course, birthdays we will anticipate it before, and we will try to send gifts, and to know whether it is absolutely separated or future, you can think of, is it possible to reach this event E2 by something which is sent from E1. Something which is sent means it may be a parcel of gift which you are sending from E1 which reaches E2, or it may be just a wish message which was sent from E1 through the light signals. Both are possible. Say the wish message sent by the sent using radio waves or the light signal from event E1, whether they are possible to reach E2 at least, even though if the gift doesn't reach, at least the photons, whether they will reach or not, we will see. The word lines of the photons emitted from E1, they themselves are the wish messages. They will tell how the E2 is future or is it absolutely separated. If E2 is the future of E1, then you can influence the event E2. Influence means if the birthday present reaches in time, then the mom will be surprised and she will be more happy. And if the birthday present doesn't reach the event E2, then she may be disappointed and the event E2 will be a different scenario. or at least if the wish message sent through the radio waves, if it reaches E2, of course that also influence. By just seeing the wish message, she may be happy at least even though she couldn't send the gift, at least I could get a wish message from the daughter, so the mom may be happy. So now we will see how it is going to be. Now whether all these things are possible, means whether the gift can reach E2 or whether the wish message can reach E2, all those things depends on how E1 and E2 are separated in Minkowski spacetime. Remember how E1 and E2 are separated in Minkowski spacetime. If it is in physical spacetime, it is not taking care of time. Here it is Minkowski spacetime, it takes care of time, and it also tells you how much time you have to reach event E2 so that you can influence the event E2. Let's see. So now for example, the event E2 is here. Event E2 is here means you can see that event E2 will happen at time somewhere around the 8. We will put it to 8 itself. Okay, we will put it here. Right here. So now event E2 is going to happen at the position 9 and at time 8. Remember, it is going to happen at position 9 and time 8. It is the event E2's Minkowski's coordinates. And now of course 8, 8, all those things are in light second. Remember, we did it in class that the axis of this Minkowski spacetime were usually taken in light second, otherwise they will be incomparable. We are talking in the relativistic speeds. So right now the packing of gift, let it be at 2, 2 coordinate, means the daughter packs the gift at time 2 second at location 2, at location 2 light seconds from the origin. So now we will see whether we will change it. Okay, so let the packing of the gift or the dispatching of the gift happens at the location 4 at time 2. Now let us see. Now she dispatches the gift, as well as she is going to send a wish message. Those wish messages are photons which are emitted from the event E1, and let's see how they will travel in the Minkowski spacetime. Right, you can see this line, purple line, is the light signal which is sent from event E1. Now you can see that the light signal reached the location of event E2 well before time. You can see here, this is the time at which the light signal reached the event E2. See here, it is somewhere around 7. So the light signal reached the event E2 before, means she got the birthday message before the birthday, so mom will be happy. And now if the daughter sent the gift with such a speed that it forms the word line, this dashed word line, then the gift can also reach the event E2. And these pink lines are actually the light cone emitted at event E2, just for the representation I have just taken. So right now this is one scenario. So now the another scenario is here. We will run it again. Right, so now the wish message she sent, and the wish message is going to reach the event E2 right in time. And of course the wish message is a light signal. It travels at the maximum speed, that will be the speed of light, and nothing else can travel at that speed, so her gift cannot reach. But her wish message can reach because it's a light signal. If her gift has to reach, then the word line, the line which you are talking here, should have slope in such a way that it is within this light cone, within this blue light cone. Means if the event E2 is anywhere within this blue light cone, so then you can send, at least you can think of sending the gift with this particular appropriate speed. Of course, you should choose appropriate speed so that the gift can reach the E2. And now if the event E2 lies here, then we call E2 as the future of E1. Future of E1 because the E2 can be at least thought to be reached by sending something from E1, either at least light signal or by something else you can reach E2. It is possible, so hence E2 is the future of it. If you see the E2 in an opposite direction here, we call it as E2 as the past of E1. And of course you can think of a backward light cone also. You can refer to the books for backward light cones. You have to just extend these light cones backwards so that we call it as the backward light cone. So right now, if the scenario is here, if the event is here, then this event is called as absolutely separated. Why? Because event E2 cannot be reached by event E1 even by the light signal also. Now let's see. Right, so these are the light signals emitted by the event E1 and this is event E2. And event E2 happened way long before the onshot of the event E2. Now you can see here, you can just read the coordinates here. The light sent by event E1 reached the location of event E2 at here, at this point. So this point is somewhere around 9 seconds, but the event E2 is somewhere around the 4 seconds. So hence the light itself cannot reach the location of event E2. Hence E1 and E2 are called as absolutely separated. In this case, you cannot influence the event E2 by event E1. So hence they will be absolutely separated. And when the events are absolutely separated, their time ordering can also be different. Means we have seen in the class that you can have a different Lorentz transform coordinates where the order of E1 and E2 can be changed also. Right. So if the event E2 lies anywhere outside this light cone of the Minkowski's in this blue light cone, then all those things are inaccessible by the event E1. So all these events are called as the absolutely separated events. And the event E2, if it is within this light cone, then all those things will be accessible by E1, and we call these things as the future of E2. Means the event E2 we call it as the future of it. Now the displacement, E1 to E2 displacement vector or the displacement in the displacement interval in the Minkowski space-time, that for this situation will be time-like. Means if E2 is within this light cone, then it will be time-like. If it is here outside this, then it will be space-like. So right. Okay. So now these events are called as now absolutely separated, and the displacement vector in this case will be space-like. And this is space-like, this is time-like, and if the C2 lies exactly on this light cone, then we will call it as the null-like or the light-like. Okay, that's it. So now somebody were asking the question, if the word lines are intersecting, whether one event can influence the other event. So now the light cone emitted by the event E2 is intersecting with the light cone of E1. In this situation, E1 cannot influence E2. And only in the case where if the light cone of E2 is enveloped inside the light cone of E1, then it's possible that E2 can be influenced by E1. So in this case, the word lines of the light emitted by event E2 will not intersect this. Of course, they will go parallel. This line and this line, the purple line and this pink line, they will go parallel here, and this cone will be inside this blue cone. So this will clarify the problem. So this is all about the light cone at a given event, and the events which are absolutely separated, absolute future and absolute past, and the word lines. Thank you.